Yeah, right there. I think that's she's telling me that. I was like, I know, no one ever. I think you'll kind of.
Okay, so today is our last class to go. That's a regular class. We'll be here Wednesday and Friday. But this is the last day for me to impart knowledge to you. So I hope I don't overwhelm you. Okay. And on Wednesday, we'll review for the Wednesday test. Okay. On Friday, we'll review for the final. Remember that the final is the ACS standardized exam for over the whole year. And so, yeah, you can't forget that old stuff. But really, we've been using it all along. So, I mean, I don't think that you should make that feel daunting. What's going to be daunting is there's going to be stuff in there that we didn't cover because that is life. I can't cover everything. I can't. You notice we didn't get through all 5,000 chapters in the book, did we? Okay, so what will happen is to grade the final, I will go through and I will say, yep, that we fixed that. And I figure out how many questions you can answer. And then I look at that number and I look at the number to get 70% correct. Whichever number is the lowest number, that's the number that your test will be out of. All the rest is extra credit. Okay? Every time I do it that way, and then every time I check, the 70 percentile is always less. Okay, so we're covering plenty. Okay, so don't think that you can't get a 70 percentile ranking on the top. Okay, I don't remember what the number is. I'll try to find out by Friday. I just can't remember. Maybe 40. There's 70 questions, I think. Okay, that makes you feel a little better? Okay, Friday we'll do an old exam, okay, and we'll do questions, and there's going to be, like, you have to get 5 right, and then everything beyond that's going to be extra for clicker, okay, on Friday. Okay, that makes you feel better too? Okay, I know this is a stressful week. It's a stressful week for us too, so, yeah. Okay, I haven't even looked at the papers yet, so don't. I have to write all the tests first. What? This final exam is Wednesday at 11 to 1. Okay? You will have 2 hours to do it. Okay? And it'll be 11 to 1 on Wednesday. I don't know where it's going to be yet. I don't know if I can do it in 202 or not. I can't. Well, it would depend on if the other classes, there's a class meeting there now, which is why we're not in there. And so it depends on when if their final is the same time, we can't use it. They'll be into it. I know. What can I say? All right, so let me make sure this is recording. I think it is. Okay. Not that anybody else cares to know all that stuff, but. Okay, here we go. What? Trying to make sure you got this. Do you have an assignment due? But you've all already been working on these, right?
Yeah, of course. Just 30 questions.
Some of them are so easy, though.
Yeah, some of them, I don't know if we covered, like the McCafferty. Did we cover that?
The McClafferty?
Yeah.
Oh, that was in the mass spec stuff. That's in there?
There's IR in there.
There's IR in there, McCafferty.
McClafferty.
Yeah, I was looking all through 18's thing, and I was like, I don't know where this is at.
I couldn't find it.
Look in your IR stuff and look in your mass spec stuff.
Okay.
It'll help you just review it. It shouldn't be 2,000. I thought I went through all the questions though, and I didn't remember those. Maybe I missed those. Y'all, it's A. Okay. It's the Bart reaction. Remember? All right, how about this one now? Right. I got 15. Isn't there 16? Okay. We're all there. Oh, you guys, we did this one last time.
Maybe we have the same answer this time.
All right, what is the difference between the two questions? This question and this question.
What's the difference?
Yeah, what's the difference in the molecule? This is an alpha beta unsaturated carbonyl. That's why it doesn't go to the carbonyl carbon. If the double bond wasn't there, if it was this, y'all had problems with this last time, so. Okay, if it looked like that, you would get this, the ketal. Okay, are you seeing the difference? Because you got to see that. Okay,
So if it doesn't have that thing into the left.
the
then it
double
would've been-
bond. Yeah.
Okay.
If it doesn't have a double bond there, okay, then it adds like to make a regular step. Okay. Yeah, like if it was a green yard or something else, that would go to this carbon. Yeah. So remember that if you're a weak base, you go to the beta carbon of an alpha beta unsaturated system. If you're a strong base, you go to the carbon of the carbonyl. Okay. We did some of those too. Okay, so what if you're a carboxylic acid derivative like this? Okay, now notice that on this carbonyl we have a chlorine. You don't have it. Right. Do you have it? Carboxylic? No, actually I thought you had that slide. You're going to get some that you don't have. That's all right, just kind of write it down. You'll get all the pictures later today. Okay, and notice that when you have an acid chloride, or we call an acyl chloride sometimes, the chloride ion is a good leaving group. Let me make this. This is really fast. Okay, so you have your lone pairs on that O. And it's going to go here, and then what happens? Up to the up to. Okay, and then if you come back in, you make your tetrahedral intermediate. You come back in, and then chloride. And so, and then you lose the proton, and you end up making an ester. This always happens with acyl chlorides. Okay, now Look at this one down here. This one is an amide, okay? Here, our nucleophile is not going to the carbon and the carbonyl, it's going here. That's because if it went to the carbon and the carbonyl, the group that would be leaving is a strong base. And so that's how come it ends up at that spot. That's the difference. Okay, so you get direct addition when you have acid chlorides, but when you have amides, which are much less reactive, you get addition to the beta carbon of the alpha beta unsaturated carbonyl. Okay, you don't have this one? Okay, I don't know what I did. Okay, so notice that this added to this part of it. My little circle isn't very good. Okay, so let's look at this. So if you take this and you add HBr to that alpha beta unsaturated ester, look at what you get. Okay, if it added to the, if the bromide ion added to the carbon of the carbonyl, then when the O- comes back down, it's got a choice. It can lose bromide ion or it can lose methoxide. Well, guess which one it loses? Bromide, because that's the weaker base. Okay, that's how come the bromide ends up adding to this carbon over here, adds to that carbon. All right, so now look at the next one. This time, we've got an alpha beta unsaturated ester, same as before, but we're adding an amine. So where do you think the amine is going to add? Do you think it's going to, first of all, do you got the two possibilities? We're going to add here or here. We're going to add to the carbon of the carbonyl, or we're going to add to the beta carbon. Okay, so which one do you think that one is going to add to? Well, look at this thing. There, we got 3 carbons, right? Okay, so if you go back down, which group wants to leave? The ethoxide or the amide? Because it is a weaker base compared to this base. Okay, so this should be your product. Okay, you just foiled me. I really thought it was the other one. Heck if I know. Don't worry about it. Let's just move on. My God, it's the end of the semester. I'm going crazy. Well, yeah, I don't know. I'm kind of upset because I really thought you can make amides from esters. I don't get it. All right. Well, yeah, we'll just move on. All right. Have you seen this? Did you see this at all in the homework? The CO thing? Do you have that slide?
No.
What do you have?
You want to look through them?
We did all those. All right, we have this. We have this here. This is coming. That's the next 2 slides. Okay, so this uses carbon monoxide and HCl to make aldehydes from benzene rings. Okay, it only works on activated derivatives. So what does that mean? That means that your group that's on your benzene ring is giving electron density to the ring. Okay, so this will work, OCH3 will not work. Okay, so it does not work on deactivated rings. Give me an example of a deactivating benzene. Give me an example of a deactivated benzene.
Nitro.
Nitrobenzene. That's the easiest one to remember. Okay. So you're using carbon monoxide. Okay. It's weird, isn't it? And so your benzene ring goes to the C of the carbon monoxide and out to the O, and then you end up protonating with the HCl down here. Okay. It's kind of weird. But the you need the AlCl3 and the copper in there to be like your little Lewis acid capsule. Okay. I'm not worried about them. Just know that it does that because I think that it shows up in your homework. That's why I thought I'd put that in. All right, this you got.
Yeah.
Amen. Okay, so oxidation of aldehydes. You can use very mild reagents. And when you oxidize an aldehyde, what do you get? There's only one thing you can get, a carboxylic acid, okay? So one of the very mildest ones you can use is silver oxide, Ag2O. Okay. You can oxidize aldehydes in the presence of other oxidizable functional groups. What would be another oxidizable functional group besides an aldehyde? What else can you oxidize? You can typically oxidize alcohols, right? 2 ketones and aldehydes and carboxylic acids, okay? So, but you can use the silver to do only aldehydes, okay? This is how they make it up. You use this silver ammonium salt, OH minus and water. And it's called the Tollen's reagent because Tollen came up. Okay, and what happens is when you do that reagent, when you use that reagent, the aldehyde gets oxidized, but remember something else always has to get reduced. Redox always goes together. What gets reduced is the silver. Okay, here it's Ag+. Well, what will happen is it will become silver 0, and when it's silver 0, it's the pure metal, and it will coat test tubes and stuff. And this has been used as a test for aldehyde functional groups. Okay, so if you did this, you would end up getting the carboxylic acid. Now, the Tollen's reagent is basic. So if you wanted to isolate your carboxylic acid, you would have to add acid until you got it acidic enough, like a pH of 2 or more, or 2 or less, I should say, in order to get the carboxylic acid. Okay, if you want to ask. And here is a picture of the silver mirror on a nice big old flask. Okay, you can do it in a test tube though, and the test tube gets silver, and it's pretty cool, really. So this is what you get is this carboxylate here, and then you have to add acid to that to get it to the. This is a nice mild way to get carboxylic acids from aldehydes. You know. All right, so here is our silver. Okay, and when it has a little arrow down, you've seen that before, haven't you? That means it's coming out of solution. It's like precipitate. The little arrow, it's an old thing for them. Maybe they don't use it very much anymore. I don't know. It's an old thing though. Okay, so sulfur nucleophiles can also react with thiol or with aldehydes and ketones to form thioketals and thioacetals. Okay, so it's exactly the same kind of thing, except you have sulfur in there. One of the problems with using them is that they're stinky. Okay, you can use the dithiols similarly to the dialcohols, just like we did before. This one has 3 carbons. So notice that Bart has 3 carbons in there instead of just 2. Okay, the thing about these is that once you get that sulfur on there, you can get rid of that using an old reagent we talked about a while back called Raney Nickel. Okay, Raney Nickel replaces the sulfurs with 2 hydrogens. So if you needed a real mild way to take a ketone to a carbonyl to a CH2, you could do this. Okay. Raney Nickel is that nickel aluminum alloy. I told you the story about how it lit on fire in a little suction filter thing. That was kind of exciting, little fires coming up. Because you have to make this up and then use it on your deal. Okay, so anyway, this is real mild way to do some of these things is with Raney Nickel, even though you have to go through the excitement of making it. Okay, I'm going to draw some molecules. I want you to tell me what is the most acidic hydrogen. Okay, okay. All right, so I'll write them in black. Okay, look at the top one and tell me what is the most acidic hydrogen in that compound. There's only 6 hydrogens, and they're all the same, right? All right, so it's got to be one of those. Okay, so if you add a base like NaOH, NaOH will work. Okay, you can remove one of those protons. What do you get when you do that? I'll pick the one on the right just because. So I'm going to get this, an H2O, and your sodium ion will be your counter ion for that. What can you tell me about that thing? What can you tell me about that? Anything about that anion that's special? Stabilized by resonance. Okay, remember when we talked about enols? These are enolates. The only difference between an enol and an enolate is a hydrogen. Enolates typically get formed because you're pulling a hydrogen off with a strong base. So you get enolates. Okay, all right, look at the next one. We're going to do something with them in a minute. What can you tell me about this one? Which one do you think is the easiest proton to pull off now? You have choices now. Which one? Be brave. The one on the right. Nope. Be braver. The one in the middle. Okay, what's the difference between the one in the middle and the one on the right? They're both bicarbonyl, but the one in the middle is by 2 carbonyls. So each one of those carbonyls is going to do. Okay, so if you add NaOH to this, you will get that. And that anion is going to be stabilized by resonance here, and then you can go the other way and go to the other one. So more resonance, more stable. Okay, this is also an enolate. Okay, once you make enolates, you have made carbon-based nucleophiles. Okay, and so a carbon nucleophile can then be alkylated. So if we take this and we add methyl iodide to it, I should have moved this one down. What are we going to get? Well, this is your nucleophile over here. So I'm going to go to the carbon and I'm going to lose my iodide. Just a simple SN2 reaction. And we're going to get What if I added methyl iodide to this one? What's going to happen? Our carbon nucleophile is going to go to the carbon, and we're going to lose the iodide. So what did we just make? Okay, could we do it again? Yes, we could do it again. What if we added NaOH to that? Which proton is it going to remove? We got more choices now. What do you think? Which proton is it going to remove? The same one, basically, this one. Okay, so now we'll have here, I'll make it a little more spaced out. This enolate, stabilized by resonance on both sides. Okay, so now let's add ethyl iodide. Two carbons. Okay, so let's add ethyl iodide. All right, so we're going to get, so we're going to have an ethyl and a methyl on the middle. What if you did another equivalent of base? Now what would happen? Is there any more in the middle? No, so you'd have to take off one on the end. Okay. Sometimes when they do these reactions, I guess I have to slide. When they do these reactions, they don't put anything else in there. Okay, so here's our acetone. We're going to add our NaOH, and we're going to remove a proton. Right? We're going to make our enolate. Okay. Ready to see the resonance? Where do you want me to draw it? Worried about you. You're getting real quiet again. I know you don't have slides. Kind of rough. All right. So we don't have anything in here but acetone. If you're a nucleophile, where do you react at the acetone? We're going to go from here to here. See what we did? Instead of just putting a methyl group on or a little simple alkyl group on, we added to ourselves. Okay? All right, so let's add to ourselves. Now what do we got? Okay, that's what we had. We made a new bond here. So I'll just make it right like that. Match what I drew. All right, and then here I'm going to have see what we did? Okay, we have water in there. The water can protonate that. And we have now condensed two things together. So a lot of times these are called condensation reactions. Okay, so we'll protonate that with water. That will give us okay, now when you look at the molecule, the way I drew it down here, do you see the two acetones? You see that here's one acetone and here's the other acetone that we did. we put them together, okay? If you heat that molecule up, okay, just like even warming it, some of them do it just almost spontaneously, but they do it pretty easily. So I'm going to put a little heat there, okay? You lose water. The water that you lose is this and one of those. What will that make between these two carbons? You lose the OH and the H. What will you have made? Go away, little box. There. I got it. Okay. So I'll have CH3, C double bond O, CH double bond C, and my two methyls. How does that relate to those other compounds? It's an alpha beta unsaturated carbonyl. Okay, everybody see that? Alpha beta. Okay. Now, when you look at this, can you see the two acetones? Here's one, and this is from the other one. Okay. All right, we're going to do another one. Okay, I'm going to stick with my acetone because I'm hoping you get comfortable with it. Okay, I'm going to add my NaOH, and I'm going to add a lot of it, like a whole equivalent. Okay, there's my enolate. Hang on. Okay, now instead of reacting with the acetone, I'm going to put something else in. So I'm going to put in there this compound. Okay, what is that compound? What is that called? Benzaldehyde. Let's go for those easy questions. All right, now what do you think my enolate's going to do? It's going to go to the carbon here, out to the L. All right, so what do I have now? Okay, that's from the acetone, is now connected to what, where? Where are we connected? To that C, right? Okay, what's on that C? NH, a benzene ring, and what else? O minus. All right. It will get protonated by water. All right, so you'll get this. Sometimes they skip this step and they don't always show it. Okay, what do you think? This one, you hardly have to heat it up. Like room temperature, it's probably going to lose the water. Okay, we'll talk about why. Okay, so what do you make now? We make that. Now do you see it's double, single, double, single, double, single, double, single. See how conjugated it is? The more extensive the conjugation, the molecule wants to do that. That helps make it stable. Now, you see the two pieces in here. Here's from the acetone, and here's from the benzaldehyde. Okay? You can even do this with aldehydes, but not benzaldehyde. Okay? So if you had this compound, that compound, okay, Notice that what hydrogen is going to be the most acidic hydrogen? This one is, right? Okay. Everybody see it's not that one. Okay, it's not that one. All right, so we're going to add base, NaOH. Okay, so we're going to get CH3, CH, CO. Okay. Oh, my H kind of lost its line. Okay. What if we only use a small amount of base, so we didn't use a whole equivalent? That means there's going to be some of this in there to react with itself. So let's react it with itself. Where does it go? To the this is my nucleophile. It's going to go to the carbon of the carbonyl, and we're going to go out to the O. All right, so can you draw what you just made? Ooh, my C is crazy. All right, so that's the first one. So I've got my bond here, okay, and that goes to the carbon of the carbonyl. Here is my ethyl. Here is my OH and my H. I'm going to just skip. All right, now, where am I going to lose my water? Here's my OH, and where's my H? Okay, so what do we make in the end after we lose the water? So we're going to have CH3, woohoo. Okay, and then here's going to be your H and your ethyl. So are you seeing the pieces? Here is the first aldehyde. Here is the second aldehyde. See where they're coming from? All right, let's take that aldehyde, and instead of adding it to itself, let's add it to benzaldehyde. The one that we used in that other one. So this is going to be your aldehyde. And we're going to add NaOH, woohoo, and benzaldehyde. Okay. So the NaOH is going to pull off a proton. What proton is going to pull off? One on the CH2. Good. So we're going to get, sometimes you have to kind of write out part of the mechanism to try to figure out the structure of the products. Okay, that's what we get from the base. And now we're going to add it to this. I should have written it in black. Okay, so now we're going to go from here to here and out to the O. Yolk gets protonated, and then you lose water. But let's draw the intermediate. So we're going to get CH3, CH. Okay, so this is my new bond from here to here, and this is O minus. It gets protonated by water, so you get the OH, and then you lose water when it warms up. Doesn't look like a bond. This shouldn't have been there because that's gone now. I'll erase it so it looks good. Okay? Are you seeing the two pieces? The condensation reactions are not very hard once you get in your head that you make a carbon nucleophile, you add to the carbon-carbonyl, you lose water. That's basically how every one of them goes. All right, let's see if I can't fix my little picture for you. So when you get it printed out later, it'll look better. Okay. Okay. Are you seeing the pieces? This is the first aldehyde. This is the second aldehyde. Okay? If you did one that was, this is propionaldehyde. If you did propionaldehyde plus butyraldehyde, you would get like a ton of mixtures because one could be the nucleophile to add to the other. So pretty much we don't do that, okay? Because you could get a negative of this plus the other one, or you get a negative off of the butyraldehyde plus that one, or plus each other. So this, what they would do is they would try to work it so that you would add one equivalent of base to try to get all of the acid-base reaction, which is faster, to occur quickly so that you don't have any of this left around to add to itself. Okay? If you want to add to yourself, then what you do is you go ahead and just use a percentage, and then it just slowly goes. Okay? Or you wouldn't add more than 50% base. Okay? But this one, you'll notice you can't get an enolate out of it. Okay? So when the two compounds are adding together are different, it's called a mixed aldol. When they are the same, it's just called an aldol condensation. Okay? So this is a mixed one. Okay, now I'm going to show you another one that's related to this. Okay? So what if we have that? What is the most acidic proton on there, you think? What's the most acidic proton? Yeah, the one in the middle, because it's still going to be stabilized by the carbonyls, by resonance. Resonance always wins. Okay? All right, so let's add our base. The only difference between this and the other one is that, what do we got here? Esters. Okay? We got us some esters. All right, so we're going to get oops. Okay, so there's my negative. Okay, now you can do different things with this. You can add it to another carbonyl compound. You can add it on just a plain alcohol. Let's do that first. So let's add. Okay, I like iodine. He doesn't get used for much. All right, so we're going to go to this carbon, and the iodide leaves, right? So what do we have at this point? Okay, so what do I have on that C in the middle now? I have an ethyl, right? Okay, you know anything about esters? Take esters and go to carboxylic acid type. Do not. I thought you might have done that in lab. Okay, You add NaOH and heat it up, and you have to add one equivalent. Well, actually, you would have to add two in this case, because what do we have on both sides? Right, okay. So what will happen is you will get, I kind of wrote big, let me do this. Okay, you will get I'm going to write ET. Is that okay? We're feeling kind of ET-ish today. Okay, we will get that. So we hydrolyze both esters. Okay, we hydrolyze both esters. When you hydrolyze esters with base, there's a word for that. It's called saponification. I don't know if you've run into that. They talk about that when you make soap. That's what you're doing. You're saponifying esters to make soap. And you get these little carboxylates, okay? Now, those carboxylates, because it's under basic conditions, we're in base, they are O minuses and A pluses. And that's what soap is, basically. It's just big, long chains. All right, now, if we take this and we add acid, what are we going to do? We're going to protonate both sides, right? Okay. So let's protonate both sides. Oops. No, I did it. Okay. All of a sudden, I thought I wrote ET twice. All right. So now, if you take this and you heat it up, look what happens. What did we do? What did we do? What's the difference between that and that? We lost the carbon, the C double bond OH. We lost one of the carboxylic acids. This will only happen when you have a carbonyl. Here's your carboxylic acid. It doesn't matter if you have two carboxylic acids, just so long as you have at least one. And then over here, you have to have a carbonyl, beta to the carboxylic acid. Okay? And what happens is you end up losing carbon dioxide gas. Okay? All right, you ready to see how it does it? We got 5 minutes. We got 2 minutes for me to show you how it does. Okay. Is that enough time? Okay, I'm going to count. 1, 2, 3, 4, 5, 6. That's the magic. Okay, is the 6-membered ring that can be formed. Okay, and so we're going to end up going and grabbing the proton. That goes there. That goes there. All right, so at that point, looks like this. Oops, I wrote too many lines. I'll do this and then I'll take it off later. See that? Okay, what is this compound? Enol. It tautomerizes to the keto form. See how it works? Kind of a nifty, fun little thing. Okay? You don't have to have 2 esters. You can do it with just 1. Okay? I got 1 minute. I'll show you one more example so that you have one. That's that way. All right, so I'm going to add and you can use a variety of bases. This is just like NaOH, it's like, so they'll do 1 and they'll do 2 and we'll go propyl iodide. We'll be wild and add another carb. All right, so what do you have now? What do I have here? The propyl group, right? Okay, now we'll add the big equivalent of NaOH. Okay, and what is that going to give me from here? That's going to hydrolyze your ester. All right, I'm going to write PRO just to make it simple. It's not proline, no. Okay. All right, and then I'm going to add acid and heat. And what do we get? The acid protonates that. Because it has a carbonyl beta, you lose CO2. So what is the beauty of carbon? Okay, and the removal of this proton is a whole lot easier. You're going, well, anybody thinking, well, let's just start with acid. That's a lot harder. This proton is more acidic than the one because there's 2 carbonyls. So you don't have to add as much base. You can be a little sneakier. Okay, it's a little simpler to do. All right, are you going to be okay? All right, I'll get all this posted for you today. Wednesday is review. I wanted to do it more. I didn't get to get you handouts, so we didn't do it. What are you doing up here?
Doing some extra.
Oh, I'm telling you.
Always working.
Okay.
So this.
Oh, yeah.
Good.
Okay.
I wasn't sure about that down integration.
That happens. It has to do with this. When you phase this, you actually are phasing that. And so, I mean, the only thing you can do is go in there and try to phase it a little more and get it a little better. But you could just try to level them off and see if it works.
Okay.
Yeah.
And then this
Okay.
one is not going to add them. And it has way too heat, so the integration is good.
Okay. So we've got.
Yeah, I mean, I've got it pulled up. There should be, I believe, 7.
Wait, did I do too many?
Yeah, you've got an extra card here.
Ah, okay.
Right.
There we go.
Yes.
Yeah. So you should have a doublet. Okay, this will be a doublet.
Right.
That should be 3 hydrogens.
Right.
This one is going to be a quartet. That's 1, and then you're going to have this one. Whether these split each other, they usually don't. But so this is.
That's a nice quartet.
That is a nice quartet. Does that work out to be 1 if this is 3? See, I'm wondering if there's ethanol in there.
Very well be.
Like this is maybe this one, but because it's smaller and it's farther downfield.
Right.
But if you had ethanol in there,
Right, it should also be that.
right, and this would not be as far downfield as this one.
Okay.
So, because this one's got the benzene and the O affecting it. So I would think that would be the one that you were looking for. And then your OH is in there. So it looks to me like you're contaminated with ethanol, which
So
might
I
be
should
part of the
wrote
reason
that.
people were having a hard time getting the solid out of it.
Yeah,
Wasn't this the one we had the hardest time with?
Yeah, I never.
Okay, did this work?
What do you mean?
This
What?
is one of them. Let's
I
see, 1,
just
2,
printed.
3, and 1. Well, they almost look even. Maybe it's these 2 are showing up together, and then these 2, because these 2 are going to be more affected by the nitro. So maybe because they look even to me.
Right.
So like 2 and 2, and this looks about half. So that would probably be your 1. somewhere in here is going to be your OH. It's hard to say which one because I bet one of them is ethanol. And then this one is probably that. Yeah.
Okay.
Yeah. So you're getting there. I think it's there. It's just not as clean
Okay,
as
yeah, I don't think.
we would have liked. Yeah.
So,
Yeah. People were having a hard time. It'll be interesting to see if the people who got the crystals, if theirs shows this stuff too.
okay, I'll look at Gabby's.
Yeah, look at her.
Did
Did she get the crystals? She got crystals.
She did get crystals, yeah.
Okay.
So, can you show me how to fix these?